Hello, everyone. Welcome to today's live broadcast, Theory and Practice of Developing LC Methods with Solid Core Particle Columns. I'm Laura Bush, the Editorial Director of LCGC, and I'll be your moderator for today's event. We're pleased to bring you this webcast presented by LCGC and sponsored by MacMod. A company should be able to condense its mission statement into a simple phrase. MacMod's mission statement is Smarter Chromatography. But you may ask, just what does smarter chromatography mean? It means that when they make a recommendation to you about an HPLC or UHPLC product, it's to partner with you to offer innovative solutions to your complex problems. MacMod uses advanced state-of-the-art analytical software to match their product portfolio with your separation needs. They leverage their 30-plus years of experience in the LC column business, the company's technical expertise, and their manufacturing network to help you solve your toughest application problems. They provide up-to-date and accurate technical catalogs and reports from industry-leading separation scientists to keep you informed of new technologies. Before we get started today, we have a few housekeeping announcements. First, the webcast is designed to be interactive, so we encourage you to ask questions. You can ask questions at any time by typing them in the Q&A box, which you can find on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the webcast. And if you have any technical problems viewing or hearing the presentation today, please click on the question mark Help widget in the dock at the bottom of your window. I would now like to introduce today's speaker. We are very pleased to be joined today by Gemma Lowe. Gemma Lowe is a key part of the business development team at Advantor UK and is responsible for leading a wide range of HPLC and UHPLC training events and seminars across Europe. Gemma has over a decade of experience working in the HiChrome technical support team, troubleshooting chromatography methods, recommending suitable column chemistries, and supporting the vast range of HPLC and UHPLC columns in the portfolio. Originally a biochemist, her focus areas include the analysis of biomolecules by various chromatographic techniques and the analysis of polar analytes. Gemma, thank you for joining us today. Please get us started.
Thank you, Laura, and thank you very much to MacMod for inviting me to speak today with regards to solid core particle columns and how we can develop methods on them. So I've decided to split the presentation into two parts. The first part will look at the theory of solid core particles and why we are so excited about this sort of technology. The second part will look more at method development and really things to consider when we're developing methods on a solid core particle compared to a fully porous particle. So in terms of the solid core technology, this isn't new. It's been around for quite some time. The first discussion about superficially porous particles was back in the 1960s when Professor Horvath mentioned the technology. And then the first generation of commercially available solid core phases was launched in the 1970s. However, more recently, with the advancements in instrumentation and the more discussion around such areas, we've really seen a resurgence and more introduction of very small solid core particles that we can then use for our HPLC and UHPLC method development. So this has really been in the last 10 years or so, and when you look on the web for references, you'll see that there are many, many people investing in this technology. The main reason for doing this is the high efficiencies, the fast methods, the potential for transferring existing methods onto a different platform, and also the low back pressure. So all of these come hand in hand with the solid core particle technology. The most recent introduction of particles was in the 2-point-something micron size, so between 2.4 up to 2.7 micron particle size. And this particle size gives us efficiencies that are comparable to sub-2 micron fully porous particles, but with the advantage of using HPLC pressures. That means we don't have to invest in new instrumentation. We don't have to purchase a UHPLC system to be able to achieve sub-2 micron efficiency. And that really is beneficial in terms of runtime and really seeing more from your sample. So there are big gains in investing in or evaluating a solid core type particle. You can speed up your method development as well when you use these solid core particles compared to a fully porous particle. And I'll show you some examples of why this is and how we can reduce the run times in our methods so that we can get more methods out the door in a quicker time frame. And I'll reference some papers, but there has been a lot of development work in this area in the past decade, so I can't give you a complete overview of the technology in such a short space of time. So for those of you that are not familiar with this type of solid core particle, what you have is you have a solid core bead, so a glass bead or a fused silica bead at the center of your particle. And then you have a coating which is porous around this solid core. And the chromatography takes place in that outer shell. So your analytes cannot penetrate the solid core. Therefore, you have a shortened diffusion path, and the chromatography only takes place within that core of the particle. As I mentioned, more recently, this 2.4 to 2.7 micron particle size has been favorable. You can also get a 5 micron particle size, which is beneficial if you want to perhaps transfer a pre-existing method from a fully porous particle to a superficially porous particle of the same dimension. So those are available. And you can get even smaller and smaller particles. I've heard today that a new one has been launched within this 1.3 to sort of 2 micron range. So those are very small solid core particles. Issue with having something that small is then you start to get higher back pressures. So the key advantage to using something 2.x is that you can run these on HPLC instrumentation without needing to invest in new technology. One thing to note really is the fact that these particles have a rho value. So the rho value is the ratio of the solid core diameter with the particle diameter. And this gives us a feeling of how porous a particle we are working with. And that's important because you'll see from different vendors, they have different ratios of core to coated, and therefore you might get different loadability in terms of the surface area is different, and also scalability of that sort of particle. So why does this type of architecture give us more efficiency, faster run times, and lower back pressure? So hopefully we'll answer some of those questions. And I couldn't really talk to you about solid core particles without showing a Van Deventer equation. So for those of you who are familiar with chromatographic theory, this graph describes the pathway of our analytes through a column. So all of our analytes of one type will not move in exactly the same way through a column. They will choose different paths, they will have different diffusion, and that's why we get band broadening of our peaks. It's why we don't get nice, sharp GC type peaks. And this Van Deventer equation really explains what's happening within the column. It is made up of three key terms, the A term, the B term, and the C term. And you can see how they contribute to the equation at the top right. And this is giving a resulting HETP, so height equivalent to a theoretical plate. We want that to be as low as possible. So the lower the height equivalent to a theoretical plate is, the more efficient our column is. So the ideal place to work chromatographically to get the optimum efficiency would be the bottom of this Van Dienster curve. And one of the big things about these solid core particles is the shape of this curve, and the positioning of the curve is different compared to its fully porous counterpart. And it's lower in a lot of cases, which means we get higher efficiencies, and the C term looks to be flatter. I think when this technology was first introduced, everyone said, oh, the C term is really, really flat with these solid core particles, and that's the explanation as to why we get higher efficiencies. But a lot of work has been done since their introduction, and we now have more evidence that the B term is the highest contributing factor to reducing the height equivalent to a theoretical plate. So in terms of what these three parts of the equation mean, the A term is the eddy diffusion. So this is the path through which the analytes take through the column. And if you have a very narrow particle size distribution, you have a very uniformly packed column, then that narrows down the different paths that your analytes can take. That means that you have a potentially reduced A term. It's not flat like we kind of draw it, but for these purposes you can assume it's relatively flat. The B term is more about the diffusion of the particles longitudinally, and my colleague has a really good way of explaining this. So if you go shopping with children, the faster you move, the closer all the children stay with you. So at really low flow rates, low linear velocity, there's much more diffusion than there is when you're going at faster flow rates, higher linear velocity. So that's how the B term works. And this is the factor that we think has the most contribution in a solid core system to reducing that height equivalent to a theoretical plate, and therefore the efficiency is higher because of that B term. The C term is related to mass transfer, and again, this is why we suspected or hypothesized that the C term was the most significant contributor when looking at a solid core particle versus a fully porous, because now we have much shorter diffusion paths. And for large molecules, this still is a very strong variable. So if you're working with proteins, you're working with big molecules, then having a shorter diffusion path will really be beneficial in terms of how high a flow rate you can go. So a thinner core on a thinner shell on a particle is really beneficial for those types of molecules. It's not the biggest factor when we're looking at small molecules. And I think this slide really describes those features I was mentioning. We have a very narrow particle size distribution when it comes to these solid core columns. The packing material is more uniform, and therefore we can pack the columns perhaps better than we could with a fully porous particle. In addition to that, there's a lot of discussion about the roughness of the particles compared to a fully porous particle. So if you actually look at the SEM images, you can see the shape is slightly different. Maybe the surface is rougher for this type of technology, and therefore that could contribute to a different packing. But as I mentioned, the B term really has the most significant effect when we're talking about solid core particles. So this is helping us to improve the efficiency by reducing the analyte molecular diffusion. and therefore we're getting better efficiencies. So if we actually look at an inverse Van Diepte equation with some real particle sizes and two different formats, you can see the bottom trace here. So along the x-axis we're looking at flow rate. So as you can see, for an increased flow rate you will get a reduced efficiency. Efficiency is our y along our y-axis. So for a 3 micron particle size, that has the lowest efficiency, but it's pretty flat to a degree the higher the flow rate you go. The next highest efficiency is our fully porous 2 micron particle. So I'm getting more efficiency by reducing the particle size. That's obvious. That's why everyone has been investing in UHPLC systems and UHPLC columns. Smaller particles give you higher efficiency. We know that what they also give you is higher back pressure. And that's why we have to invest in such technology in terms of the instrumentation and the packing technology for the columns. So the highest efficiency actually is gained by using a solid core particle. So this 2.5 micron particle has the highest potential efficiency. It's 38% higher than our 3 micron fully porous particle. So you can see the data speaks for itself. It is beneficial to move to a solid core particle, even with a slightly bigger particle size than your sub 2 micron particle, to gain efficiency while not paying with so much back pressure. And the next slide shows you the back pressures that are generated by these 3 different particle sizes. So the lowest back pressure is generated by a 3 micron packing material. The highest back pressure is by that 2 micron fully porous packing material. And our 2.5 solid core sits nicely in between, giving us gains in efficiency and lower back pressure compared to the sub 2 micron fully porous particles. So we can say these 2.5 to 2.7 micron particles generally provide similar efficiencies to their fully porous sub 2 micron counterparts. However, they give you lower back pressure. And that's the take-home message. We can use these columns on our HPLC systems. And there are still many, many HPLC systems in use. Not everyone owns UHPLC systems. So when we're thinking about how this can help us, another thing we can think about is the speed of analysis. And there's 2 reasons, really, why these solid core particles give us faster run times. The first one is kind of related to what I've shown you already. So we can use higher flow rates at a given efficiency, which means that to gain the same chromatography, we can do it in a faster runtime and get the same sort of N numbers from our peaks. So that's one way of speeding up the method. The other reason is the fact that we don't have as much surface area within our solid core particle. So you can't actually bond as much C18 to a solid core particle as you could to a fully porous particle. Got a lower surface area, and therefore you can't add as much bonding. That means that it's less hydrophobic. And I'll show you some examples proving that's across the board. Whoever manufactures it, everyone has a lower hydrophobicity when it comes to the solid core equivalent to the fully porous phase. If you want to move from your standard 5 micron fully porous phase to one of these, 2.5, 2.6, 2.7 micron solid core columns, then what you can do is trade in some of that extra efficiency by reducing the column length. So obviously the efficiency of the column is related to the length of the column. I can throw away some plates and that will give me a shorter runtime. So again, there's many ways that these solid core particles can really help us to speed up not only our method development, but our assay at the end of the day once we've developed that method. When we think about our gradient methods, we think about average peak capacity. And if you've got more efficient separations, so you've got sharper, narrower peaks, then you can fit more peaks into a separation window. Now, you have to bear in mind that these particles could potentially be less hydrophobic, so the separation window is not quite as big as for a fully porous counterpart. But in most cases, you can get a greater peak capacity, and therefore...
Gem, I think you just cut out for a moment. So maybe you could just back up a few sentences. I'm hearing you again now. Thank you.
Okay, no problem. I will go back to the start of this slide, talking about peak capacity.
Sounds good. Thank you.
Excellent. Thank you, Laura. So when we talk about our gradient methods, we talk about average peak capacity. And normally, for a more efficient separation, we have a sharper peak. Sharper peak, narrower peak means we can fit more peaks into that separation window. Now, you might have less wide a separation window with these less hydrophobic particles. So, as you know, in reverse phase, we're mostly looking at hydrophobicity as the dominant mechanism of interaction. If you have a less hydrophobic phase, you might have less retention, less K prime within your gradient method. So it is a balance, but generally we can get a greater peak capacity with these solid core particles. That gives us an improved signal to noise. We've got taller, sharper peaks, therefore that's better in terms of the sensitivity of a separation than the fully porous 5 or 3 micron counterparts of a fully porous nature. And I just wanted to give you an example of how you could transfer a method from a fully porous 5 micron packing material to a solid core 5 micron packing material. So the top chromatogram here is a fully porous 5 micron material. And the only difference that we made when we ran the method on the solid core column shown at the bottom of the slide is that we changed the sampling rate of the detector. So we actually turned it up from 2.5 hertz to 20 hertz so that we could fully describe each peak. And we scaled the injection volume because, as I mentioned earlier, we have less porosity on a solid core phase. So for an accurate translation, we should be injecting less onto these columns. And what you can see is a reduction in runtime. So my initial method at the top, the last peak comes out at 20 minutes. The new method on a solid core equivalent column comes out about 9 minutes. And the efficiency of those later eluting peaks, in this case it's an isocratic method, so you've got much higher efficiency, nearly double the efficiency of that final peak in the chromatogram. And this is based on the reduced hydrophobicity of that solid core phase. Even though they've got the same chemistry, they've got the same bonding on there, you've got less hydrophobicity on that solid core phase. So you are reducing the runtime that way, but you're also getting big gains in efficiency. So for a given efficiency, you can use a higher flow rate and reduce your runtime. What you pay for, what you pay with, is back pressure. So if we just look at this fully porous 2 micron particle here, you can see for a certain efficiency, so just over 150,000, your flow rate is 0.5-ish, you can get 73% faster runtime if you move to the solid core phase for the same efficiency. So you can speed things up by having the same efficiency but using a faster flow rate. The back pressure is higher, but it's not as high, for example, as if you were to try and go that fast with a sub-2 micron particle. Now, as mentioned, reverse phase is predominantly a hydrophobic interaction with our analytes. And one way in the past we've chosen to speed up methods is to reduce the length of the alkyl chain on our stationary phase. So instead of using a C18 as our starting point, we've gone for a C8, for example. So we have a less hydrophobic stationary phase, and that has given us a faster run. If we need more separation, then we could look at C18 chemistry instead. Or if that's still too long a runtime, we could go to a C4. The only mechanism there is that hydrophobic interaction of our alkyl chain on our stationary phase with the hydrophobic part of our analytes. So you can easily demonstrate this by reducing the chain length, so reduced hydrophobicity leads to reduced runtimes. You can see that clearly here if you look at the runtimes. The elution order is the same. Maybe the selectivity is a little bit different, so the peak spacing is slightly different with a difference in chain length, but the runtime is shorter, and you've got reduced hydrophobicity based on the lower carbon loading for a C4 column versus a C18, for example. And if you then go to solid core particles and you look at the solid core column versus the equivalent fully porous column, you'll see that the surface area is lower and then the percentage carbon load is lower for any vendor that you look at. And this is just because of the particle architecture. So this means that we have less hydrophobic solid core phases, meaning we can, in theory, have much faster runtimes when we develop our methods on this type of technology column. And that leads me nicely into method development for the last section of this webinar. And really, when I sat and thought about how we would go about developing a method with a solid core column, all of the considerations are the same as I would have for a fully porous phase. You know, I need to think about the pressure. Can I use an HPLC system, or do I need to use the UHPLC system? What size column am I going to choose? And there's differences because I'm looking at a solid core phase compared to a fully porous. So it's not the 3, 5, 10 micron that we've historically had. I've got some differences in particle size, pore size. Column chemistry, massive influence on selectivity for method development. And when we first started talking about this technology, people brought out 2, 3, 4 phases. Most vendors have a much higher offering now. So there are pretty much all of the same chemistries you can get for reverse phase on a solid core platform as you can get with a fully porous platform. We also need to think about what solvents, so acetonitrile, methanol, what buffers, what modifiers we're going to use in there, what temperature, what pH. So everything you would be considering normally for a fully porous phase. One thing just to bear in mind if you want to do more of a transfer of a method is that you have a different porosity on these solid core columns compared to a fully porous column. So you need to consider injection volume, flow rate, gradient, and instrument setup if you're moving, say, from a 5 micron fully porous to a 5 micron solid core. So when we talk about method development, We know and love this resolution equation. It is our greatest friend when we're developing methods. It's our greatest enemy if we don't control it during our QC. It's made up of these three components: efficiency, selectivity, and retention. And they each have their own contributing factor. If you put it graphically, you can see that you need retention of your analyte. This is the K value shown in green. Retention values between 2 and 10, 2 and 20 are fine. If you have too much retention, you are leaving analytes on the column for too long. You're not actually gaining anything in terms of resolution or separation of your analytes. Efficiency is a stronger term. So you can see the blue line here is a steeper gradient. And improving efficiency by reducing particle size, by using longer columns, that can really help us in our method development. But the most powerful term in this equation is the alpha term, is the selectivity term. And there are many factors that influence selectivity. And we need to think about those very much when we're doing our method development. We tend to use selectivity in the first stage for our method development, and then look at the efficiency as a tweaking, to get the best optimization of the method at the end. So we choose a dimension column to work with for method development, but potentially once we've chosen the right selectivity, then we could change the column dimension. We could throw away plates, or we could add get a longer column, for example, to get higher efficiency when we optimize the method at the end. So when we look at selectivity, we think about alpha, and this is a separation factor. So this is for two adjacent peaks. We want these to not be co-eluting. We want these to be separate, ideally baseline separation, so that we can touch the baseline before the next peak starts. You need to have a selectivity value, so an alpha value above 1 to be separating out the peaks. It doesn't need to be that much higher than 1 to improve the separation, but it does need to be above 1 for our chromatography to really be achieving what we want it to, so to be pulling those peaks apart. And your system will be doing this for you in the background. It will give you values of retention, K, and alpha, so the ratios of two adjacent peaks, the K values of two adjacent peaks. So from a practical standpoint, we can change a number of factors that affect alpha, that affect selectivity. And we've listed these nicely at the bottom of the slide. So for isocratic methods, the column type is the strongest influence. So do I choose a C18 or do I choose a phenol? If you've got ionizable analytes, which to be honest most of us have, then pH has a big impact. That's the buffer of the mobile phase that you choose. Make sure you do choose a buffer. The type of organic modifier has a big influence. You can see significant changes in selectivity if you move between acetonitrile and methanol, for example, especially if there's some pi-pi interactions with the column. And then other factors affecting the selectivity are the percentage organic modifier, the choice of buffer, the temperature, and the concentration of the buffer for an isocratic method. If you're running a gradient method, you have to think about the actual gradient slope as well. So this K-star equation is really important. It includes the gradient time, the flow rate, the range of the gradient. So am I going 5 to 95, or am I going 10 to 80, for example? And the column dimensions, so the volume of the column. We can assume for small molecules, M is a constant of around 5. Other things like the dwell volume and the column dimensions, therefore, have an impact on selectivity as well. So as I mentioned, when you change the length of the alkyl chain on a stationary phase, you change the retention time. You don't really change the selectivity to a massive degree. You don't have a different mechanism there. It's just hydrophobicity. But if you go to something with a different type of bonded phase, so for example, a cyano phase in this case, or a phenol, you've got different interactions. And those different interactions then give us big changes in elution order. So instead of my analytes here coming out 1, 2, 3, 4, 5, they are eluting 3, 1, 5, 4, 2 on a cyano phase, and 1, 3, 2, 4, 5 on a phenol phase. And that's because you've got different mechanisms of interaction. pH has a big impact as well. As I mentioned, for ionizable compounds, pH can have dramatic changes in retention time, elution order, and therefore selectivity. And it depends whether you're working with a neutral molecule. So you can see here, along the x-axis, we have the mobile phase pH. Along the y-axis, we have our retention time. So for a neutral compound, here shown in green, changing the pH does not have a massive impact on the retention time. That's pretty obvious. But if you're working with acids and bases, you have much more of a change in retention when you change the pH. And what we can do is choose points within this mobile phase pH to look at which analytes elute first. So here at a low pH, we have good retention of our acid. You know, lots of us will start our method development at low pH, especially if we're working with acids. So we get good retention of our acid, that comes out last. Our neutral analyte is always coming out at about 10 minutes in the middle. And our base is poorly retained, coming out early. If you move to an intermediate pH, then our neutral analyte doesn't move. Our acid is now pretty poorly retained, and our base is a bit better retained. So they're all nearly co-eluting somewhere in the center of that chromatogram. When you start to work at high pH, now our bases are much better retained, coming out later in the chromatogram. Our acids are poorly retained, and our neutral doesn't move. So it really is key to choose the right pH depending on your analyte type. And we don't always have the privilege of knowing the nature of our compounds. We can work out the nature of our compounds based on how they move related to changes in the pH of our mobile phase. But it is something really worth exploring for method development. It's a really powerful tool in method development. And the worst place to work is on one of these high gradients where very small changes in your mobile phase pH leads to significant changes in your retention time, because that's not going to be a robust method. You're going to have such stringent controls on your buffer that it's not really viable to then put that into a QC environment, for example. So most of the method development examples I'm going to show you are on this 2.5 micron solid core particle structure that we have, and with two different bonded stationary phases. The first one is a C18. You know, C18 works for the majority of applications with this hydrophobic interaction. In this case, it's a super C18. What that means is it has an encapsulated bonding technology to extend the pH range. So actually, I can not only exploit the two different stationary phases, but also I can exploit pH when I'm doing my method development. So this phase is good between pH 1 and pH 11. So it's more extensive than our standard silica-based materials. The same goes for the superphenol hexyl. So instead of having just a straight alkyl chain, now we've got some aromatic interactions, potential for pi-pi interactions, hydrogen bonding, dipole-dipole potentially. So you've got some more polar interactions with that phenol hexyl type phase. And when you're doing your method development, the easiest place to start is with that one column. The one column you have in the drawer, normally a C18. You try one temperature, one pH, one organic modifier, and one gradient slope, and you see what you get. And you can build up more complex method development protocols, adding more and more of the variables that affect alpha as you go along, depending on your experience and your time and the method needs, really. So if you had all the time in the world, potentially you could work through each of these parameters case by case, keep adding in different columns with different technology, different pHs, different modifiers. But it would be helpful if we didn't have to do so many wet runs. So we tend to look at two columns, so two different types of stationary phase with different mechanisms of interaction. Two different organic modifiers, and methanol and acetonitrile are fantastic solvents for HPLC. So we look at those, and in this case we've looked at two different pHs. You can look at more, and if you've got a more limited silica pH range, for example, you could look to stay within the pH range for those columns. But here we're looking at pH 3, so low pH, and pH 10.7. And using that, we get a good selectivity space. It's a two-column method development screening approach based on the selectivity that we know. Start at low pH, broad scouting gradient based on a K-star value of about 3. So our favorite column dimension is 100 by 3. And that's what we tend to use to give us a good idea, a good starting point when we're doing any method development. And we tend to look at Uwe Neuer's work for comparing parameters within chromatography. So if you run a set of probes down one column under a given set of conditions and record the retention times, you then do exactly the same set of analytes, the same set of probes under the same set of conditions, but on a second column, then you can plot the corresponding retention times and get a scatter plot. The more similar those two columns, the straighter, the better the fit will be than a scatter plot. The more different the parameters, the two columns are, for example, the more scatter there will be within the plot. And that gives you a selectivity value. Higher selectivity values mean more difference in retention times for your analytes, so more difference in alpha, more difference in selectivity. So we did this for two different stationary phases on a solid core platform, and you can see when you compare the plot for these two different columns, you get some scatter, a selectivity of 19, which gives you a decent selectivity space to work with. And when you look at that chromatographically, you can see in the top chromatogram, the elution order is 1 through 23 on a C18 column. And then under the same conditions on a phenyl hexyl, the peaks are all moving around. You've got a very different picture just based on changing the stationary phase chemistry. So that is a very powerful way to develop methods by looking at two very different stationary phase bondings. Potentially, then you could look at pH on the same stationary phase. So here I have the phenyl hexyl running at both low and high pH with our methanol mobile phase. And that gives us a much bigger scatter in our selectivity plot. So now we have a selectivity value of 83 when we compare the two different pHs. And what that shows chromatographically is again a significant change in selectivity, significant change in alpha. It's what we need for our method development activities, move our peaks around, and therefore hopefully separate them from each other. It's a massive selectivity space when you look at pH. but you have to have a stationary phase capable of working at that pH. Finally, you can change more than one variable. So here we've got a C18 versus a phenyl hexyl, one at low pH, while the other at high pH. We've also changed the organic modifier. So this is changing all three of those variables, looking at the entire selectivity space that you saw in those three boxes to give you a selectivity value, in this case of 85. So it's the biggest number that we've seen in changing variables to have the biggest selectivity space. And that gives you the best option, or the best chance of separating out all of the analytes in your sample, which is what you're trying to achieve with your method development. So different stationary phases, different pH, and different organic modifier can be a fantastic platform for method development. And you can do it really quickly with these solid core phases because of the fast run times and the low back pressures. Just a couple of examples here, comparing a C18 versus a phenyl hexyl. Big changes in selectivity, especially for aromatic compounds in this case. And again, you can just choose one column that is capable of running at different pHs and do like a pH switching experiment, because the results you'll see are quite extreme, because it changes the ionization of the analytes. It moves all those peaks around. I'm conscious of time, so I just wanted to mention a couple of other things when it comes to solid core phases. The first one is loading. I've said a few times you've got less surface area in a solid core column, therefore you should be injecting less. You can overload these columns, not to the degree that was reported really in the early stages of launch, but it is worth bearing in mind, especially if you're looking at purification activities. Potentially these have a lower loading capacity than for a fully porous equivalent. And again, in our case, we have a different rho value for a 2.5 micron to a 5 micron column particle size. So the scalability isn't there. That means that if you want to develop your method on a 2.5 micron particle, you might need to tweak it when you go to a 5 micron particle. And again, that's something to consider for preparative chromatography. The final thing is that these columns work on HPLC. They work on UHPLC instruments. But if you don't have an optimized HPLC system, so you've got an old instrument that you've put together from different pieces and has a lot of extra tubing, potentially a lot of extra column band broadening, then you may not gain all the benefits that this technology offers you, especially if you go for a small ID column. So do try and optimize your instrument so it has low extra column volumes. You don't have any extra tubing that you don't need. The flow cell is the right size for very small peaks. The sampling rate is turned up to cope with very small peaks as well. I remember working with a group who should have had fantastic chromatography, but it wasn't described fully when they actually ran the method because the sampling rate was too low, so all their peaks looked like potatoes instead of nice sharp peaks. So in conclusion, I think solid core columns give you speed and efficiency for your separations. To develop a method, you just need to think of the same parameters that you have for your fully porous columns. Screening is really beneficial, especially if you can throw in pH to that screening. If you can find a phase that is stable over a wide pH range, then that works nicely in exploring, fully exploiting the selectivity space. Lots of the speed improvements are based on the reduced hydrophobicity of these particles. And do be aware that your instrument plays a big role as well. So making sure you've got fresh connections, you've got good fittings, you've got narrow bore tubing, all of that will help to give much better chromatography. And we have a lot of fantastic resources that you can tap into. If you go onto the MacMod website, if you go into their resources section, then you can see, you can download knowledge notes, translation tools, and these are really good technical articles that can really give you a more comprehensive insight into some of these areas of chromatography that I've kind of just touched on today. So use those resources, and of course do speak to us if you have any specific questions. With that, I would like very much to thank MacMod and LCGC for having me, and pass the mic back to Laura. Thank you.
Thank you, Gemma, for that excellent presentation. Before we move to the Q&A session, we have 2 brief polling questions for everyone in the audience. In each case, please click directly on the screen to enter your answers. So here's that first question, which is now on your screen. Would you be interested in learning more about ACE ultra-core columns? Yes or no? So again, you can click directly on your screen to answer, and that question is, would you be interested in learning more about ACE ultra-core columns? Yes or no? All right, fantastic. Now we'll move to our second question. Do you feel that you learned something new about solid core particles or method development today? So once again, click directly on your screen to enter your answers. And that question is, do you feel that you learned something new about solid core particles or method development today? Yes or no? All right, fantastic. Thank you everyone for answering those questions. It's now time to move to the question and answer period. As a reminder, if you'd like to ask a question, you can do that by typing it in the Q&A box, which you can find on the right-hand side of your presentation window. So let's take a look at the questions. So here's one for you, Gemma. Can I just switch from a 5 micrometer fully porous C18 column to a 5 micrometer solid core column, also C18, and get the same results?
It's a good question. In terms of the chemistry, yes, you've got a C18 in both formats, and ideally, if it's from the same vendor, then it is possible to switch from the fully porous to the solid core. I would bear in mind there are changes, as I've talked about, with hydrophobicity. There are potentially changes in the hardware of the columns as well, so that might play a slight role. We have a really good translator tool that I mentioned in one of the previous slides, and you can download from the MacMod site. And that really shows you the things that need to be modified when you're transferring methods. So it is predominantly the injection volume, so you scale the injection volume based on the different porosity of the columns. But also, if you're running a gradient method, you've now got a different volume column, so you need to maintain the same K star, you need to make sure that you are scaling according to the different column volume. And you can do that manually, but since we've developed this translator, it's good to try that to help transfer the methods across. And just another thing, the pharmacopoeias, so the USP, the EP, a lot of them are recognizing now that you can use both a fully porous particle or a superficially porous / solid core particle within the monograph and still actually be following the guidelines of the monograph. So yes, in theory you can, but it makes sense to change just a few sections of your method to make sure it is an accurate translation.
Thank you, Gemma. So here's another question about switching columns. If I change to one of these solid core columns from using a fully porous column, will it get blocked up more quickly?
It depends on which particle size you go for. One of the great benefits of using solid core technology is the narrow particle size distribution, and that means that for a 2.5 micron packing, for example, we can still use the same Fritz that you would be using for a 3 micron packing. That means that you don't have to use really fine filters at the top of the column like you would for a sub 2 micron packing, for example. So in theory, if you're using something 2.x, then it shouldn't get blocked up. again, it depends on your sample. If you're injecting horrible, dirty samples, we would always recommend the use of guard cartridges. But if you're not blocking up your fully porous 5 micron, then you won't block up your solid core 5 micron. So hopefully that answers the questions.
Thank you, Gemma. What is the interparticle porosity of superficially porous particle columns?
The interparticle porosity. So I'm trying to interpret this. It will depend on the density of the column packing. I don't have data on that. It's not like a monolithic type column that would have an interparticle porosity, I would say. So the between particles will be very similar to what you're getting for a fully porous phase. These are packed as tightly as possible. Most of them are packed at double the pressure, you're going to be using them at. So they're going to, it's an interesting question. But it should be pretty uniform throughout the column if you've got these nice uniform spherical solid core phases. I don't know if there's any articles on that. That would be interesting.
Okay, thank you. Do you have any applications for cannabinoids?
We have done quite a lot of work on cannabinoids in the past. So we had a paper at HPLC, a poster at HPLC last year on the solid core phases for cannabinoids and looking at terpenes as well as cannabinoids. So that was quite an interesting application area, and I know that is a growing area of interest. So definitely these highly efficient peaks can be really beneficial when you have lots of different isomers of cannabinoids, for example. So yeah, we definitely have a poster on that that we can forward on.
Are these solid core columns compatible with an Agilent L1260 Prime 2?
I don't know the back pressure rating of the Prime 2 off the top of my head. A standard Agilent 1260, I mean, that is going to have a back pressure of 600 bar, maybe higher. It's all to do with the flow rate you choose. So yes, you can run them on any instrument, and the flow rate you choose should stay within the back pressure limits of the instrumentation. I would imagine, I mean, we've run these on different vendors' instruments. We've got 1100s, we've got 1200s, we've got 1290s. So the different Agilent modules, for sure, you'll be able to use that type of technology on, as well as every other vendor that is out there.
Great. I think this person's clarifying and saying up to 800 bar. I think that must be what they're saying.
Oh yeah, 800 bar.
The instrument is. Okay.
Yeah,
Great,
definitely.
Do you have any applications of compounds with molecular mass up to 2,000?
So most of the work we do is under 5,000, and we'd say that a 90 angstrom pore size, which is pretty standard, for this type of solid core particle, will be fine for a 2,000 Dalton molecular weight. I'd call that a small molecule. When you get above 5,000, that then tends to need a bigger pore size. There are vendors out there that offer larger pore size solid core phases as well. So the molecular weight really is not a limitation for solid core technology. So yeah.
Fantastic. Gemma, well, I think with that, we'll wrap up. Thank you so much for your talk today and for answering all those questions.
No problem. Thank you for having me.
I want to thank everyone in the audience for attending and participating in today's event. And I'd like to thank our sponsor, MacMod, for making today's webcast possible. You'll receive an email alerting you when this webcast is available for replay. We invite you to forward that announcement to your colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.